You know, in the race to build our future, scientists are on this constant global treasure hunt. But they're not looking for gold. Nope, they're searching for new materials, compounds that can completely unlock the next generation of technology. And today, we're going to dive into one of those treasures.
So what if I told you that there might be a single substance that could tackle some of our absolute toughest problems in both computing and energy? It sounds a little like science fiction, I know, but a recent study has put a major spotlight on a very real and very promising candidate.
Because, let's be honest, our current technology is starting to hit some serious walls. I mean, just think about all the heat your computer or your car engine is constantly kicking out. That is valuable energy just vanishing into thin air. And at the same time, we're pushing the physical limits of how much data we can possibly cram into tiny spaces. These are the big bottlenecks scientists are desperate to break through. All right, let's meet the star of the show. It's a type of material called an antiperovskite. And these compounds are already known for having some really interesting electronic and magnetic properties. This one's got a bit of a mouthful for a name. Calcium carbon nickelide. We're just going to call it CaCNi3. So let's see what makes this stuff so special.
And here it is. This is what it looks like on an atomic level, the fundamental building block of CaCNi3. You can see the calcium, carbon, and nickel atoms all lined up in this super precise repeating cubic pattern. And that perfectly ordered arrangement? Well, that's the foundation for all the fascinating properties we're about to talk about.
But look, before you can even dream of building a computer chip or power generator with something new, you have to answer the most basic question of all. Is this thing actually going to hold together, or is it just going to fall apart? Stability is, without a doubt, step one. And this graph right here pretty much gives us the answer. It shows the material's energy level at different volumes. The only thing you really need to know is that nature always seeks the lowest possible energy state. So that big dip at the bottom of the curve, that's the material's sweet spot. That's its most stable, most natural form.
So the takeaway is simple. The calculations show CaCi3 is structurally sound. It passes that first most important test with flying colors. This thing is a solid foundation you can actually build on.
Now this slide gets into the why. Why is it so stable? This is basically a map that shows us where the electrons are hanging out. See those bright red and yellow areas? That tells us there's a high concentration of electrons, and they're forming really strong bonds, a mix of what scientists call ionic and covalent bonds. It's this complex glue holding all the atoms together that gives the material its unique bag of tricks.
Okay, so let's move on to the first big application. Remember that problem we talked about with all that wasted energy? Well, it turns out CaCNi3 might have a really cool solution.
It all comes down to this fascinating bit of physics called the thermoelectric effect. It's actually pretty simple. If you heat up one side of a material like this and keep the other side cool, it generates electricity. That's it. No moving parts, just a natural flow of electrons.
And think about what that means. We could literally stick these materials on industrial exhausts, on car engines, or even inside our own electronics, and just capture all that heat that's being wasted and turn it right back into useful power. It's basically like recycling energy itself.
So the big question is, how good is calcium-magnesium at doing this? Well, scientists measure that with something called the figure of merit, or ZT. You can just think of it as a scorecard for performance. The higher the ZT number, the better it is. This graph shows the ZT value at different temperatures, and you can see the peaks where it's most efficient.
And the peak performance they found in this particular study was a ZT of about 0.26. And get this, it hit that peak at a very high temperature, 1,000 Kelvin, which is over 700 degrees Celsius.
Now, a ZT of 0.26 might not sound like a world record on its own, but the real key here is the temperature. So many other materials just break down or stop working at that kind of extreme heat. The fact that CaCNi3 actually performs well up there makes it a really strong contender for industrial settings, where you find tons of high-temperature waste heat just waiting to be harvested.
But wait, there's more. Turning heat into electricity is just one of its talents. This material also has some pretty surprising properties that could be a huge deal in the world of data and electronics.
To get this next part, we need to talk about something called spintronics. So try to think of an electron not just as a particle with a negative charge, but as a teeny tiny spinning magnet. Spintronics is this revolutionary idea that wants to use the direction of that spin, whether it's up or down, to represent the ones and zeros of our digital data.
And this is a fundamental shift in how we do things. Right now, all our electronics work by just pushing electron charges around, which, as we know, generates heat and uses a lot of power. Spintronics, on the other hand, would just flip the spin, which promises to be way faster, much smaller, and a whole lot more energy efficient.
And this graph, this is the smoking gun. It's showing us the energy states available to electrons with spin up versus those with spin down. Just look at it. The blue and red lines are not symmetrical at all. There's a really clear imbalance, which means the material has a natural preference for one spin direction. And that imbalance, that's the literal definition of a magnetic material, which is absolutely crucial for spintronics to work.
So the bottom line from the research is that CaCNi3 is both metallic, meaning it conducts electricity, and it's ferromagnetic, meaning it's magnetic. That incredible 2-for-1 combo makes it a prime candidate for building the spintronic devices of the future. Things like ultra-dense and super-efficient hard drives.
Okay, so let's just step back for a second and put all of this together. It's pretty clear that CaCNi3 is not a one-trick pony. This is a material with a surprisingly diverse and really powerful resume.
So here it is, the final report card. We know it's structurally stable. It's also mechanically ductile, which basically means you can shape it without it breaking. Super important for manufacturing. It's got those promising thermoelectric properties for turning heat into power. It's ferromagnetic, which is great for spintronics. And as a cool little bonus, the study also found it's a strong absorber of UV light, which hints at even more potential uses in optical electronics.
And hey, you don't have to take my word for it. The researchers themselves concluded that CaCNi3 is, and I quote, a truly versatile material with potential that spans across multiple, cutting-edge fields of technology.
And that's exactly why this kind of deep dive, foundational research is so important. This one paper basically lays out a detailed roadmap of this material's properties, and it gives other scientists a clear starting point to begin experimenting with it, tweaking it, and hopefully engineering it for all sorts of real-world devices.
It really makes you wonder, doesn't it? I mean, if a single, relatively simple compound like this can hold so much potential, what other incredible materials are still out there, just waiting for us to find them and unlock the next chapter of our technological future?